Good morning, everybody. So before we finish up chapter 9, let's talk just a moment about this molecule. What is it? It's benzene. What's special about it?
Very stable.
It's aromatic, right? So we know it's an aromatic compound. So what do we know about it? We know it won't do addition chemistry, at least not readily. And we know that it likes to do electrophilic aromatic substitution, right? That's what we know so far. So if I wanted to take benzene and I wanted to make nitrobenzene, what reagents do I need?
Nitric acid.
AlCl3.
Not yet. That's for a different one.
Nitric acid and
Nitric acid and sulfuric acid, right? So HNO3, H2SO4. So the electrophile is what?
NO2.
What's E plus?
NO2 positive.
Right? I'll put that in quotes. So we can take that to nitrobenzene under those conditions. What if I wanted to make bromobenzene? Now, Selena, what were you?
AlCl3.
Not the AlCl3, a different Cl3, or Br3. Yeah.
What are we trying?
We're trying to convert benzene to bromobenzene. We need bromine.
And FeCl3.
Br3. Yeah. Remember, this has to be the same halogen as what you're trying to put on, right? Now, if I wanted to make toluene or methylbenzene, now I would use AlCl3 and what?
Methyl chloride.
Yeah, I could use chloromethane, yeah. That'll work just fine. Notice I'm putting a lot of these things in quotes because they're really not that. They act like that, but they're not that. What about if I want to take this and convert it to the ketone? I want to use AlCl3 again. And what? Almost a carboxylic acid. It's kind of like a carboxylic acid, except it doesn't have the OH. What does it have instead of the OH? Cl. Yeah, acid chlorides. Right, and this behaves like, oops, the positive charge there, but it's not really that. It's not a carbocation. Right? We talked a little bit about that last time. Okay? So this is the kind of stuff that we can do quite readily with benzene through electrophilic aromatic substitution. Right? So we can make halobenzenes, we can make alkylbenzenes, we can make ketones, we can make nitrobenzenes, all pretty well. But there are some limitations to what we can do in some cases. So for example, in the Friedel-Crafts alkylation, you can't use vinyl halides. Okay? You can't use something that looks like this to do a Friedel-Crafts alkylation reaction. Notice that the chlorine here is attached to an sp2 hybridized carbon. So you can't use vinyl halides, and you can't use aryl halides. So I couldn't take this aryl halide, react it with benzene and aluminum trichloride, and get this molecule that's called biphenyl. It doesn't work. Your alkyl halide has to be attached, the halogen has to be attached to an sp3 hybridized carbon. Okay? So that is one limitation of this methodology. You are limited in the types of alkyl halides. Another limitation is you have to pay attention to rearrangements. So if you see here, we've got benzene, we've got a secondary alkyl halide, in this case a secondary chloride. We're using aluminum trichloride, and notice what happens. Notice they labeled the carbon in red here that has the chlorine. So you might predict that that carbon will form the bond with benzene, but in fact it does not. Why is that?
Rearrangement.
Why? Why does it rearrange? Why does it rearrange? Right? If you look at the secondary alkyl halide, you see the carbon in red is the one that has the halogen. You would predict initially that this carbon would be what forms the carbon bond with the benzene, but it isn't. That red carbon is not part of the carbon-carbon bond to benzene. It rearranged. Why?
More stable carbon cation.
Okay, so what happens when we put the secondary alkyl halide in solution with the aluminum trichloride?
It's gonna, the Cl is gonna attack.
The aluminum, yeah?
Yeah, the aluminum.
And what happens to that then, when that happens? It leaves, and we get a secondary carbocation. So anytime we generate a secondary carbocation, we have to think about it, right? And in fact, what happens then, once we get that secondary carbocation, is this hydrogen shifts, and you get the more stable tertiary carbocation, which is this carbon right here. That's why you end up with that carbon-carbon bond. And this can even happen with primary halides. Okay? So if you look at a primary halide and you did this reaction, you won't get that primary carbon-carbon bond. It'll go to the secondary. Okay? And that's because you can get a rearrangement. Now you might be asking, well, I didn't think you can generate a primary carbocation, and you're absolutely right, you can't. But as the chlorine is reacting with the aluminum, this takes on kind of like a carbocation, almost like a carbocation, and the hydrogen shifts and kicks the chlorine off. Okay? So you got to be very, very careful with these rearrangements. Always pay attention to where your halogen is. Okay? Another thing that you need to think about is any carbocation can do Friedel-Crafts-like chemistry. Okay? So we've already learned several ways in which we can generate carbocations. I can take an alkene, I can react it with sulfuric acid, I can protonate the alkene in a Markovnikov fashion. Doesn't matter here, of course, because the carbons are the same. And I get a carbocation. That carbocation will react with benzene to make a carbon-carbon bond. Okay? We also know that we can take alcohols and we can react them with a strong acid. And the first step, of course, is protonation of the alcohol to get, what do we call this?
Sodium.
That's an oxonium ion. It's attached to a tertiary carbon that can readily leave and give me a tertiary carbocation. That works to do Friedel-Crafts chemistry as well. Lynn, you have a question?
Can you say that part about the bromine again, that last part?
Bromine.
No, not in this. Like on
Here?
Yeah.
That doesn't happen.
Yeah, it doesn't happen. What exactly were we trying to do?
I was showing that if you have a halogen attached to an sp2 hybridized carbon, that's a limitation.
Okay.
You can't use those those aren't alkyl halides. They don't do Friedel-Crafts chemistry. Does that answer?
Yeah.
So, let's do an example. You all tell me what the product is.
isobutyl benzene.
Isobutylbenzene. So tell me how to draw that.
The benzene, and then just the four straight carbon chain, but attached on the second one.
Ah. Like that?
Maybe.
Maybe?
Yeah.
That's right. So what happens? What happens in the first step?
It's as if the alcohol is.
Yeah, so what happens in the first step, right, is the alcohol, and again, sulfuric acid, we can think of it,
H plus.
right? So we protonate the alcohol. We've done that before. Right?
And water H2O leaves.
I can leave. Very similar to what kind of reaction?
Elimination.
Elimination does that, but also when we were doing SN1 kind of chemistry, right, we'd protonate the alcohol, water could leave, right? I've got a secondary carbocation. Can that rearrange to a more stable carbocation?
No.
It can definitely rearrange, but it's not going to give me anything more stable, right? If it rearranged here, it'd give me a primary. That's no good. If it rearranges here, that would be a secondary, and it'd be the same thing. So I couldn't really tell if it ever did or not, right? Now what happens? The benzene reacts with it. How does that reaction happen?
It attacks the positive side,
And it being what?
the benzene.
Okay, so the pi bonds, right?
Yeah, the pi.
Let's see. All right, so it attacks there, so I've got to have a carbocation there, right? I'm going to have that, and I'm going to have that. Okay, and then of course I've got the HSO4 minus. Now what happens? It's not the product yet, right?
It remove a proton, so the negative charge is not, yeah.
This is nothing more than the general EAS reaction that we learned, right? So anything that can generate a carbocation can do Friedel-Crafts alkylation chemistry. Okay? But Friedel-Crafts itself, when they discovered it, was some alkyl halide plus aluminum trichloride to give the carbocations. Okay? Everybody got that?
No, 1 second.
Skip that one. Got it?
Almost.
Okay. So these Friedel-Crafts reactions are useful in a lot of different reactions. Here's an example of where a Friedel-Crafts acylation, right? So we're going to form a ketone, is used to make a ring, right? So if you start with this molecule, you'll see a benzene ring. You'll see another ring that's attached to it. But they wanted to make this 6-membered ring that was attached to the other 2 rings. And so what they did was they took this, got the acid chloride here, reacted that with aluminum trichloride, and this will then react with the benzene ring to make a new carbon-carbon bond between this carbon and this carbon, right? And now we have another ring. We've made a ketone, right? And so that's a new carbon-carbon bond that we formed. And then you can actually take this intermediate through several steps and you can make LSD out of it. And so lysergic acid diethylamide is a useful compound. It's also an illicit drug, but it does have legitimate uses as well. And so it does get synthesized in a manner similar to this, I think, on an industrial scale. All right. So let's suppose that we want to do electrophilic aromatic substitution on a benzene ring that already has something attached to it. And I'm just going to, since we're talking about NH2, I'm going to put NH2 here. Okay? Now, if I take this and I react it with something to do electrophilic aromatic substitution, right now let's just call it E+. How many possible products could I have?
All the resonance structures.
Okay? Let's not go down the resonance, you're right, but let's not go down that hole yet. How many possible different ways can I add one additional substituent to this molecule?
Basically, the ortho.
Three.
That's right. Yep, you're right. Orthomet and para. I have three possibilities, right? So if I react this with an electrophile, in theory, from what you know so far, right, I should be able to make that compound and or that compound and or that compound. There should be three possible products. However, when we run these reactions, we find that we don't get all three. And it depends on what that initial substituent is. If you look at aniline, right, the nitrogen has a lone pair of electrons on it. We all agree with that? And it's on, those electrons are on the atom that's bound directly to the benzene, right? Notice what happens. We can actually draw resonance structures. I can push that pair of electrons into the ring, so to speak. So I can make a carbon-nitrogen double bond here. I can break one of the pi bonds and put a negative charge on this carbon. I can move that negative charge around the ring. I can make a double bond between these two carbons, break that double bond, and put those electrons on that carbon. And I can push them even further. I can make a double bond here and break the double bond there, put them on that carbon. Okay? These are all resonance structures of benzene. If you were positively charged and you had to react with this group at the benzene ring, which positions would you want to go towards?
If I was positively charged,
If you were positively charged,
then a negative charge.
you'd want to go to the negative charge, right? But does every carbon atom in the ring have a negative charge?
No.
No. That carbon has a negative charge. That carbon does not in any of the resonance structures that we drew. That carbon has a negative charge, that carbon has a negative charge, and that carbon has a negative charge. What is that position relative to the nitrogen? Ortho, and that is para, and that is ortho. So anytime I have an atom that is attached to a benzene ring that has a lone pair of electrons, it's going to direct the incoming electrophile where?
Either
Ortho
or para.
and para. It will not direct it to the meta position. Okay? So, these types of things are called ortho-para directors. Okay? So, let's look at a couple of examples. If I started off with phenol, which we'll talk about in just a moment, is that going to be an ortho-para director or not?
Yes.
Yes. That will be an ortho-para director. This is an ortho-para director. This is an ortho-para director. If I started off with an ether, what is that? That too is ortho-para. What if I started off with bromobenzene?
No, it's a meta.
Why?
Because there's no longer a pair of electrons.
Does it? I didn't draw them, but are they there?
They are there.
They are there. Remember, don't forget, just because I don't draw them doesn't mean that they're not there, right? So there are lone pairs of electrons. So it too is an ortho para director. Okay? And it also turns out that anytime you have an alkyl group, like CH3, CH2, whatever, these two are also ortho para directors. They don't have a lone pair of electrons, but they still donate electrons into the benzene ring. It just can't really draw resonance structures for it. Okay, it happens to do with what's called hyperconjugation, and we don't need to get into that. Okay, so your take-home message here is any atom that's attached to the benzene ring, if it has lone pairs of electrons, it's going to be orthopara, or if it's an alkyl benzene, it's going to be orthopara. So that must mean that anything else is going to be a what? Meta-director. Okay? And let's see why things behave as meta-directors. So here's an example of a ketone, or well, I guess aldehyde, benzaldehyde. Does that carbon have lone pairs of electrons on it? No. Okay. But what does this do? This actually pulls electrons out of the ring. Okay? And you can see why here. We know that the carbon-oxygen bond is polar. Oxygen's more electronegative. You can imagine breaking that pi bond and putting the electrons on oxygen. That gives you a positively charged carbon that's directly attached to the benzene. That positively charged carbon, which we call a carbocation, right, can actually pull the electrons out of the ring shown here. So now we can break this double bond, make a double bond here. That puts a positive charge on what position?
Meta.
No. It's ortho to this, right? If this is carbon number 1, this is carbon number 2, that's ortho, right? Now I can move that positive charge by drawing another resonance structure where I break this pi bond and make the double bond there, put the positive charge there. What position is that? Para. And I can push one more time and put it here, which is what?
Ortho again.
Ortho again. Now, if Jason were a positively charged thing, where would he not want to go?
Stop the positive.
You would not want to go to the positive, right? So you are not going to go to the ortho or pair positions, you're going to go to the meta position. The meta position, by default, not having a positive charge, must be more negatively charged, right? Even though it doesn't have a formal negative charge, okay? So this is going to be what we call a meta director. That's the formal, or that's the right way to draw out a nitro, if you wanted to draw it out in a Lewis structure. Is that going to be an ortho pair or meta director? Meta. Okay. What about if I had
Meta because nitrogen is positive.
nitrogen's not positive here, it's neutral. But is there any lone pairs on this? No. It's meta, right? And in fact, I can push one of these here and make that positive. I can do all kinds of stuff. Right?
But doesn't nitrogen normally have a positive charge?
If it has 4 bonds. This one only has 3. So let's do the experiment. Well, the experiment's been done for you, right? If you take toluene and you react that with bromine and FeBr3, you would find that you get about 40% of your product would be the ortho isomer, and about 60% of it would be the para isomer. You might be able to detect a trace of the meta. I've actually done this exact experiment. I've never been able to see a trace of the meta. I only see ortho and para in approximately that ratio. Okay? Why is the ortho less than the para? Yeah, right? If the electrophile has to come in, is it gonna wanna get close to the big methyl group, or is it gonna wanna be further away from the big methyl group? It's gonna wanna be further away, right? And so that's why you get, the major product is the para. And 90% of the time, the major product is gonna be the para isomer. There are some special situations where that's not the case, but not what we're gonna be talking about today, okay? Now, if I take nitrobenzene and I put on another nitro group, notice 93% of it is going to be the meta isomer. Okay? 93% of it is going to be the meta isomer. If I take toluene and I react it with a lot of HNO3 and H2SO4, XS means in excess, it's a shorthand. So I'm using lots of it. What do you think my final product could be?
Ortho and para.
What do you mean ortho and para?
It may be both, like there are two NO2s attached in the ortho and zero. Oh yeah, three. Oh,
What's that molecule?
TNT.
Trinitrotoluene, TNT. Very explosive. This is how it's made. If you try to make it on your own, you will kill yourself. Okay? And it turns out that the first one to go on goes on para, and that's no problem. That's easy to do, and it's not explosive. The second one will go on in one of the ortho positions, and that's not even too terribly hard to do. But getting that third one on, you usually have to heat this. Okay? And as you heat it, it tends to want to go boom. And so that's the problem with trying to make your own TNT. It's a very simple reaction. All you need is battery acid, a little nitric acid, and a little paint thinner. That's all it takes to make TNT. Okay? And in fact, people that wish to do harm in the world go out and try to make this. Okay?
So, I have a question that might, well, really not. You know when people make like Molotov forms, like when they're like.
Molotov cocktails?
Yeah.
Yeah.
Is that, like, how does that work?
It's just gasoline or some flammable in a bottle with a wick.
So
So
they
when
don't
you
have to
throw it-
react with anything?
Huh?
It's just- They don't have to react with anything?
Nope. Nope. So when it hits the ground, it breaks, the rag's on fire, right? And it just catches whatever the contents of the bottle were on fire. I mean, people can make those out of fingernail polish remover, paint thinner, gasoline, alcohol, doesn't matter. A Molotov cocktail is just a generic term for a cheaply made resistance type incendiary, I think is what they call them. But no TNT. Molotov cocktails don't explode.
Well, they do when you throw them.
Actually, they never explode.
Does
They,
it?
Combust.
what do they call- they combust and conflagrate. Yeah, I mean, there's a lot of fire, a lot of damage, but it's not an explosion. Okay? So the last thing that we need to talk about in chapter 9 is phenols. And phenols are a very special class of molecules. They can undergo electrophilic aromatic substitution reactions. Okay? But they can also do other things as well. So you can take phenol and you can react it with bromine and iron tribromide, and you can get and I don't remember what the ratio is of the two, but you can get ortho and para bromophenol. Okay, that's normal kind of stuff. But the phenols actually have some other properties that are kind of interesting. So if you take a phenol and you react it with sodium hydroxide, what do you think is going to happen? What does sodium hydroxide like to react with?
Acid?
Do I have an acid?
No.
Mm.
Oh,
Mm. Do I have an acid?
maybe.
Maybe.
Uh,
Where's the acid?
Just,
is it the hydrogen?
It is.
Terminal hydrogen?
It's that hydrogen on the oxygen. And that, in fact, you can make what are called phenoxides very, very easily with sodium hydroxide. You can deprotonate. These are special alcohols. They're more acidic than a typical alcohol. Anybody know what the pKa of an alcohol roughly is?
Can I guess 15?
You can, and you'd be really close. It's about 16. Yeah, about 15 to 16. Very similar to water. Remember I said that alcohols were just organic derivatives of water, right? We know that because we can hydrate an alkene and make an alcohol. But these have a pKa of approximately 10-ish. That's a lot more acidic. You can deprotonate these things very, very easily. Okay? You all also depend on phenols. You just may not know it. So there's a phenol. It's called BHT. Okay? BHT. It's an antioxidant. Phenols typically have antioxidant properties. For those of you in nutrition, what is an antioxidant and why is it important?
Free radicals?
Free radicals. Okay, very good. What do we mean by free radicals?
Like oxygen.
I'm breathing them right now. Yeah. Molecular oxygen is a free radical. What do free radicals do to biological molecules?
Oxidize.
They oxidize. This is how you go rancid, right? As you breathe, you're getting oxidized. You're going rancid. You're spoiling, right? But your body has things, you don't have BHT in your body. You have vitamin E. Vitamin E is also a phenol. Okay? But BHT is kind of like vitamin E. And we use that to preserve a lot of things that you all might use. BHT is put in some foodstuffs. It is put into paints. Paints will oxidize and you don't want them to spoil sitting on the shelf. So this is an industrial antioxidant. Okay? So phenols have an important property of functioning as antioxidants in a variety of situations. So what happens if you become vitamin E deficient?
Hair loss?
Hair loss? You get under a situation that we call oxidative stress, right? Now, I don't know all of the processes. I'm not a biologist, right? But here's what happens when you're under oxidative stress. You start to build up plaques in your arteries. What happens when you build up plaques in your arteries? Atherosclerosis. You start to have heart attacks. You start to have strokes, right? So it's very important that you have the right amount of vitamin E in your diet all the time. If you don't, you take vitamin E supplements, right? To try to keep that vitamin E level right, or you'll undergo a lot of oxidative stress. What can contribute to oxidative stress other than the organic chemistry class? That's a joke. This would be the major sin. Smoking leads to oxidative stress. Drinking excessively leads to oxidative stress. Not having an appropriate amount of vitamin C and vitamin E in your diet can lead to oxidative stress. You all will probably learn about those things in your nutrition classes to some degree, okay? But it's very important. This little OH functional group that's attached to an aromatic ring is responsible for the antioxidant properties, okay? And you got to have it. And in fact, you can measure the ratio of vitamin E in your cells pretty easily. And you start to see that correlate pretty well with things like heart disease and stroke and even some cancers. Okay? So make sure you have your regular intake of vitamin E and vitamin C. It's very helpful. Okay, so we're going to jump into chapter 10. I think we've got time to pretty much finish this today because it's not a very long chapter. But we're going to talk about amines. We'll talk a little bit about nomenclature. I'm not going to spend too much time on the naming of amines. Mostly what we'll cover is kind of some common amine names that aren't really systematic, that are thrown out there an awful lot. We'll talk about some physical properties. Of course, we'll go through some interesting amines. Not going to spend a whole lot of time on the preparation of amines. We'll give one example. And then we'll talk about how an amine can function as a nucleophile as well. And usually we're a little closer to Thanksgiving when I teach this, but this is where we're at. So, we all know what an amine is. This is one of the functional groups you had to learn early on, right? We can have primary amines, secondary amines, or tertiary amines. A primary amine is an amine where the nitrogen only is connected to one other carbon. A secondary amine is where the nitrogen is attached to two carbons. And a tertiary amine is an amine where the nitrogen is attached to three carbons. Okay? So, what is common among all of the amines, other than the nitrogen? A pair of electrons. All amines will have a lone pair of electrons. Okay? Otherwise, it becomes a different group, and we'll talk about that. Okay? So, primary amine, secondary amine, tertiary amine. You need to be able to identify them. Okay? Amines, because of that lone pair of electrons, they can function as both bases and nucleophiles. Remember, all nucleophiles are bases, but not all bases are nucleophiles. Amines can be both. So if I take an amine and I react it with an acid like H2SO4 or HCl, it's going to protonate the amine and I end up with what we call a ammonium salt. I no longer call that an amine. Why?
Well, it's lone pair.
It doesn't have a lone pair on nitrogen anymore, does it? And the nitrogen is positively charged. It's a different functional group. This is called a quaternary ammonium salt in both cases. You all are familiar with quaternary ammonium salts, especially during COVID. What did you all use an awful lot during COVID? You used sanitizers. Some sanitizers, and especially antibacterial soaps, contain quaternary ammonium salts as a bactericide. Okay, it's not very good for viruses, I don't think, if I remember right. But it's really good. So if you get, like some Dial antibacterial hand soap and you read it, it will contain some type of quaternary ammonium salt. And they're usually made by taking an amine and reacting it with some alkyl halide, okay, and you end up making a quaternary ammonium salt. Here it's functioning as a base because it's reacting with what?
Acid.
Yeah, H+, right? It's reacting with an acid, a Bronsted acid. Here, it's functioning as a nucleophile because it's reacting with some kind of carbon, right? So what kind of reaction would this be? What would be the name of that reaction?
Substitution.
Substitution, nucleophilic. As it's drawn, is it unimolecular or bimolecular?
Bimolecular.
And why is it bimolecular?
It attacks and leaves at the same time.
Yeah, so the nucleophile, I can't point to the TV, I'm sorry. The nucleophile attacks, the leaving group leaves, that's all in the same reaction. So these things like to do SN2 type reactions quite easily, okay? All right, so if I take a primary amine and I react it with a strong acid, okay, I get this protonated amine or quaternary ammonium salt, if you will, okay? The pKa of the acid needs to be less than 10 for this reaction to lie to the right because the pKa of these quaternary ammonium salts is around 10 to 11. They're pretty easy to deprotonate, actually, okay? And so we can react these with just about any acid that you can think of pretty easily. So you can take, this is ethylamine, react it with hydrogen chloride, HCl, and I get this ammonium salt. The equilibrium lies to the right. Why is that?
Higher pKa, more stable.
Okay, what do you mean more stable? What was the rule we learned early on when we talked briefly about acids and bases? Equilibrium always favors the stronger acid or the weaker acid?
Weaker acid.
The weaker acid. pKa of 7, that's a stronger acid, right? pKa of, well, let's just call that 11. Weaker acid. The equilibrium will always favor the weaker acid. And in fact, the equilibrium is so far to the right that we say it goes to completion. That's a huge difference in pKa. This little reverse arrow shouldn't even be there, okay? But I can also react this with organic acids. What's this one called?
S. Oh, carboxylic acid.
It's a carboxylic acid,
Acetic acid.
and this is acetic acid. This is vinegar, right? This is the acidic component of vinegar, and you can actually react that with this amine. What kind of amine is this?
Tertiary.
It's tertiary, and it will do the same thing, and it will form a product, right? Where we have this type of quaternary ammonium salt. We can take advantage of this. We can use this to separate amines from other organic molecules. So let's say Jason came to my lab and he wanted to work with this amine. And let's just say he's got sloppy lab techniques for some reason, and he accidentally mixed it with this alcohol. And he came to me and said, oh, I messed up. I mixed two things together that I shouldn't have. My answer to him would be to separate this back out. We're not going to waste it, right? I know that this amine will react with strong acids to give a stable ammonium salt. Are salts soluble in water or not?
Yes.
They tend to be soluble in water, okay? Are alcohols that have a lot of carbons typically soluble in water?
No, a lot of
A
carbons.
lot of carbons, yeah. What's the rule?
5.
Yeah, so this alcohol has how many carbons for each OH?
1 and 6.
Yep, so
That's too many.
too many. It should not be that soluble in water, right? So what Jason does is he takes this and he adds it into methylene chloride. Everything's soluble in methylene chloride. And then he adds a weak solution of HCl, so 10% hydrochloric acid in water. Okay, so we know that the water layer is going to be on the top. The organic layer is going to be on the bottom here. How do I know that?
Because of the different densities.
Yeah, methylene chloride is real dense, so it falls to the bottom. The water stays on the top, and we get these two layers. He takes the separatory funnel, he puts a stopper in it, and he kind of shakes it. When he shakes it, the amine ends up reacting with the acid to give this quaternary ammonium salt, which is going to be soluble in water. The alcohol remains unchanged. Remember, this is only 10% HCl. It's not going to react to form an alkyl halide very quick, right? There's not enough HCl in that. And so the alcohol stays in the lower organic layer. So now, since he uses a separate funnel, he opens up the stopcock, drains out the methylene chloride, and that's going to be here. And then he's going to drain out the water into a separate flask, and that's going to be here. And now he has separated efficiently this from this, almost. Now what would he have to do?
Separate the salt from the water.
You'd have to get the salt out somehow. And how could he do that? Pull the water off. Could pull the water off, but I'd still have the salt, right? He needs it to be the amine. He doesn't need the quaternary ammonium salt. So what could he do? Are these acidic? They have a pK of about 10, right?
Yeah.
So what would I need to do?
Add base.
What kind of base?
Strong base.
What kind of strong base do you
Something
know?
to eliminate
Well, not eliminate.
the.
More like neutralize.
Kind of like neutralize, yeah. What kind of base do you know of?
Sodium hydroxide.
Sodium hydroxide. That's right. So what he would do is he would take the water layer, he would add some sodium hydroxide to it. That would react with the acid and make water, and it would give the free amine back. Now the free amine is going to be less soluble in water, more soluble in organic. So he's going to take the water, put it back in the separatory funnel, wash it with some organic material, maybe methylene chloride, and get his amine separated from the material. Okay. This happens all the time. We do this kind of work all the time in the laboratory. Have you all done anything like this yet in your organic lab?
No.
All right, I'll have to talk with him. We'll have to change this for next semester. But this is kind of the lab techniques that you need to know about. Okay, this is called separation by we call a separatory funnel. Okay, and we're using chemistry to do the separation. Okay, if you take this and you react it with a base, you get the amine back. You all may have heard of this in popular culture. It's called free base. Okay, what is free basing? Huh? Something with cocaine. I'm not passing any judgment here, right? What does it mean to free base? Not really.
What does it have to do?
Never heard the term free base? So when you harvest cocaine from a coca leaf, they use this kind of chemistry, all right? Cocaine is an amine. And to get it extracted from the plant, they react it with acid, and that makes it the quaternary ammonium salt that makes it soluble in water. They evaporate the water down and they sell them. But these salts, while they're water soluble, they don't cross the blood-brain barrier very well. Okay? And so what you'll do to make crack cocaine is you will take that and you will react it with Drano, which is sodium hydroxide, and that makes the free base form.
Wait, there are two different types of cocaine.
Mm-hmm.
There's one that doesn't get you high and one that.
Oh, no. They will both get you there. One just does it worse than the other. So the salt stuff is the powder. The free base is the crack. And they're both cocaine, but one is more potent than the other. But they are, so it's not like meth where you have the left hand and the right hand. It's just whether or not they're in the salt form or not. Okay? So you can see some pKa stuff here. If you take ammonia, right, and you react it with acid, you get the ammonium cation, right? Ammonia is a weaker base than, for example, ethylamine. So if you notice, the pKa for this is about 9.3. The pKa for this is 10.8. That means that this has to be the stronger base, doesn't it? Why would a primary amine be a stronger base than ammonia?
It's not positively charged.
That's positively charged.
Wait, which one?
Why is this a stronger base than this? But the pKa's are coming from the protonated species, right? I mean, this is approximately 10 times more basic than ammonia.
Does it have to do with the fact that that one's attached to 3 hydrogens, but the other one's attached to like 2 and then the CH3, CH2?
It is, yeah. It has to do with the fact that there's an organic carbon attached to this nitrogen, right? And these carbon groups actually will donate some electrons to the nitrogen and make this more basic, okay? I can't really draw a proper resonance structure for it, but we know it has to be true because of the pKa differences. So what do you think would happen if we put a second R group here? Would it be more or less basic than this one?
More
It would be more. And if I add a third, more. And if I add a fourth,
No.
no longer. Why? Because I no longer have the lone pair of electrons, right? Got to keep that right. So primary, secondary, and tertiary is the order of basicity, okay? So amines kind of have an interesting structure. The nitrogen is sp3 hybridized. It's got 3 things attached to it and a lone pair. So that's really 4 different things around that nitrogen atom. Okay? It kind of takes on this pyramid type shape. So if you look at a ball and stick model, if you have your ball and stick model, you'll see that it kind of looks like this. The lone pair of electrons, of course, is going to be here. The bond angles are about that of a tetrahedron. Right? So carbon is tetrahedral. It has bond angles of 109.5. Amine is about 108. It's a little tighter. Why is it a little tighter?
Is the lone pairs of electrons pushes them.
And what was that theory that you learned in Gen Chem?
Valence electron theory.
Yeah, we call it VSEPR, right? Valence shell electron pair repulsion. And so because we have a lone pair, that lone pair repels those bonds and makes them get a little closer together. So that it's not exactly 109.5, it's about 108 degrees. So it's a little bit of a scrunch tetrahedron, but a tetrahedron kind of nonetheless. Now you can imagine having 4 different groups around the nitrogen, right? A lone pair is a group, a hydrogen, something over here that's different than this one. That's 4 different things. You can imagine seeing a mirror image of this, and if you build the models, you'll see that they are non-superimposable. So this amine should be chiral, right? That should be a chiral center, but it's not. Well, it is, but you can't isolate R and S.
Does it have to be a carbon in the middle?
It doesn't have to be. It's just what we've been talking about. Right? I can give you any atom with 4 different things around it in a tetrahedral arrangement, it'll be chiral. And the nitrogen is technically chiral. It's got 4 different things around it. But the problem is that at room temperature, it undergoes this inversion. It'll go from an sp3 hybridized atom to an sp2 hybridized atom, and then back to an sp3 hybridized atom. So it's kind of neat that this happens at room temperature. You can actually measure this with our magic microscope. And so you always have a mixture of both the R and S enantiomers all the time. You can never isolate R amine, where the nitrogen is the chiral thing, or the S.
Even at
Nitrogen.
extreme temperatures.
Even at what?
Extreme temperatures.
I can take it extremely low and I can do something. Is
You
that-
said it was at room temperature, so that's.
Yeah, but we're talking really cold. It would have to be. But what I can do is I can convert this to the ammonium salt, and it no longer has the lone pair to invert, and so it can be separated. So if you look at the quaternary ammonium salt, these actually can be separated into R and S. There's no lone pair on the nitrogen to invert anymore.
So would they change it to an ammonium salt, do the chemistry they need to do, and then isolate it by adding the acid, like?
You could, and then it would convert. And so you do all this work, spend a lot of money, and then it would just go back to the way it was. So you'd waste a lot of time, okay? So ammonium salts, you can have R and S, but amines you really can't, because there's always going to be a mixture of 2 enantiomers, okay? All right, let's talk a little bit about some naming. Primary amines are usually named using either the systematic naming or the common name. So for example, CH3NH2, that's a primary amine. How do I know that that's a primary amine? 1 carbon attached to the nitrogen, right? Notice what's not drawn there. The lone pair, you have to know that they're there. The systematic name for this is methanamine. Methanamine. You drop the A and E ending, or the E, excuse me, ending from methane and add the word amine. That's how you get methanamine. I don't know about you, that doesn't roll off my tongue very well. The common name for it, however, is methylamine. Okay? So, for those of you who were Breaking Bad fans, this is what Walt and his compadres stole out of the big tanker truck. Methylamine.
The second you said that, I was like, that word sounds so familiar.
Yep, that is exactly what Walt and Jesse and whatever the other guy's name was stole out of the train car.
Wait, those were the things they were stealing from that like warehouse thing where they wanted people to make their.
So early on in the series, they stole from a warehouse, but then they stole from a big train tanker car
Yeah.
in later seasons. That's where the one guy shot the kid on the bicycle.
Yeah.
Remember the scene? It's a terrible scene, but anyway, methylamine. That's what you gotta have, okay? Here we have another primary amine. Why is this a primary amine and it's got a circle?
Secret.
Doesn't matter. This nitrogen is attached to only one carbon, right? So it's still a primary amine. But this is a cyclohexanamine, hard to say. So we call it cyclohexylamine. Okay? So we name it as if it's an alkyl group attached to the nitrogen. Right? Just like you said, 4-methyl whatever, 5-methyl whatever, when we were naming. Right? So now you just name this as a methyl substituted amine. You will hear me most of the time use the words in the common name format. Okay? Most chemists don't go around and say cyclohexanamine, even though that's the systematic name. We'll call it cyclohexylamine. Aromatic amines, these are also very, very important. Here's a few examples. Of course, you already know aniline. What would be the systematic name for aniline?
Benzenamine?
It was aminobenzene, right?
Okay.
Aminobenzene, but everybody calls it aniline. Is it a primary amine or a secondary amine or a tertiary amine? It's primary. Here we have what's called N-ethyl aniline. N-ethyl aniline. Is that a primary, secondary, tertiary amine?
Primary. No, wait, secondary.
It's secondary. What's this business with the N? If I said ethyl aniline to you, what could that mean?
The ethyl is attached to the benzene. whatever.
Could be, right? Right? So I could have aniline,
So that was attached to the nitrogen, or the?
and then I could have the ethyl group, right? But that N tells me that the ethyl group is attached to the nitrogen. That's why we have N-ethyl aniline. Okay? And here we have O-bromoaniline. What's the O mean? Ortho. Okay? Ortho-bromoaniline. Okay? You can also have amine-like compounds where the nitrogen is within the ring itself. Here's pyridine, here's piperidine, here's pyrrolidine, pyrrole. These are just common molecules that you should know something about. Pyridine, what does it kind of look like?
Benzene.
Kind of looks like benzene, right? And in fact, it is aromatic, just like benzene is, except one of the carbons has been replaced with nitrogen. This stuff stinks. Most amines stink. If you've ever walked into a fish market and you smelled the fishy smell, you know what you're smelling? Amines. They're all amines. The smell of rotting flesh is called putrescine. You might have heard of something called putrid. Okay? It's an amine. These things have terrible smells. Okay? But they are useful.
You can neutralize those smells.
With acid. That's
Why
exactly right.
don't they do that? The fish people, it stinks up the whole store.
Yeah, if you go into, in my opinion, if you go into a fish store and you smell it, it smells really fishy, don't be buying fish. All right, when you freshly catch a fish, it doesn't smell like fish,
Yeah.
right? It's when it starts to decompose, it starts to make these amines, putrescine, that it starts to. So if you walk into a fish store and you start to smell a really fishy smell, I wouldn't eat sushi there. Okay, I wouldn't do it. In fact, if you ever go into a good store where they've got good sushi grade fish, you won't smell a fishy smell. You just don't. Your sushi shouldn't stink. Sushi should. Yeah, that's a tongue twister. Okay. So let's look at some physical properties. Amines are very similar to alcohols in a lot of ways. You've got these hydrogens attached to something that's not carbon, just like an alcohol does. So they can form hydrogen bonds. And so you might expect that the boiling points and the melting points and all that will be different than for things that can't form hydrogen bonds. And so, but what you find is that the amines are somewhere between something like an ether and an alcohol. Okay, so if you look at the molecular weights of all these, they're about the same, right? About 74, 73. But look what happens with the boiling point. So they all have the same molecular weight. This molecule boils at 38 degrees Celsius. What's the body of the human, or temperature of the human body?
37 and a half.
Yeah, pretty close to 38, right? So if you're running a little bit of a fever, you can actually boil this molecule. This amine, however, has a boiling point of 78 degrees. You're not going to boil that away with your hand. And then this alcohol has a boiling point of 117 degrees. And it has to do with the fact that alcohols can form better hydrogen bonds than amines. Okay, so that's the reason why. Okay, and you can see this quite easily. So if you have a tertiary amine, there is no hydrogen on the nitrogen, right? Notice the boiling point of that is 38 degrees. But if I rearrange things just a little bit and I make this amine, now I have an NH, same molecular weight, but now it can form a hydrogen bond. You know, it goes up by almost 20 degrees Celsius.
So the hydrogen bond gives it a higher weight.
It does. That's right. That's why water boils at 100 degrees. If hydrogen bonding didn't exist, there could be no life. Because at the temperature of the Earth, water should be a gas. And it's not. Okay? And it has to do with the fact that it can form hydrogen bonds. And those hydrogen bonds make it behave as if it's heavier. And so you can have liquid water at Earth-like temperatures. Okay? But, you know, water doesn't weigh very much. It only weighs 18 grams per mole. Methane weighs more than that. But methane's a gas, right? And it's all because of this hydrogen bonding stuff. Solubility. Amines are going to be soluble in organic solvents. We just saw that when we did the example with the separatory funnel. Amines are going to have similar water-soluble properties as alcohols, so that 5-carbon rule still holds here. So amines that have 5 or fewer carbons for every amino group will be soluble because they can form hydrogen bonds with water. If you get to 6, 7, and 8 carbons, they'll start to be insoluble. As you see here, so anything with greater than 5 carbons tends to not be soluble in water. Okay. So let's talk about some useful amines that are not illegal. This amine right here is called histamine.
Immune system.
Huh?
In the immune system.
Yeah. What does it do for you? Allergy season, it drives you crazy, doesn't it? Right? And so what kind of amine is it? It's a primary amine. Yeah, it's a primary amine, right? And so this gives rise to a lot of physiological effects. It gives you your runny nose, your hay fever, your yada, 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 yada. Histamine's responsible for all that. And so during certain times of the year, people will take things like brompheniramine, which is this molecule right here, okay? Sort of kind of looks like this a little bit, but not quite. It's a little bigger, right? It's got some other groups on it. It's got a bromine, hence its name. But what kind of amine does it have? That's a tertiary amine, whereas this is a primary. And it turns out that this binds to the same cell receptors that histamine binds to, but it doesn't elicit the response, the allergic response that you all have to deal with. So this blocks histamine from causing those side effects, okay, which is kind of nice. And then, of course, citabidine, also known as Tagamet. This is an anti-ulcer drug, and you can see the nitrogens throughout, although I wouldn't call these really amines like this, okay? Some other amines that you all probably are familiar with, probably the most famous, right? The Starbucks molecule, caffeine, right? Caffeine is found in coffee, as you all know, but you can find it in other things as well. Coca-Cola, Pepsi-Cola, fine chocolates, all this kind of stuff has caffeine in it. You can see a lot of the amine structure, so a tertiary amine right there in the caffeine structure. Caffeine is very bitter if you've ever tasted it directly. I don't recommend you do that. It is a mild stimulant. Gives you a little bit of a increased heart rate, but it also has some side effects. People who drink a lot of coffee or intake way too much caffeine over time will develop stomach issues because caffeine stimulates your stomach to produce more stomach acid. So you might start to have things like acid reflux if you drink too much coffee. So some people will experience that kind of thing. You got to start taking antacids to help neutralize that. And of course, many of you also know that if you drink too much coffee, can't sleep. It causes insomnia at some level. Nicotine. This is the addictive molecule in tobacco. Is there any chiral centers in nicotine?
Yeah.
Right there, there's a chiral center. This is a chiral molecule. There's actually a lot of work in the tobacco industry on how you can use this molecule to make other things, because as the consumption of tobacco goes down, tobacco farmers would still like to make a living. Tobacco companies would still like to make a living. And so can we use the tobacco plant to get this molecule, which is chiral, and useful to make other things? And the answer to that is yes. So tobacco companies not only make smokeless or smoking tobacco, but they also make grow this to harvest the nicotine for other uses. The plant actually makes nicotine because it's very toxic, and it's toxic to pests in particular. So bugs like to eat tobacco leaves, but they get the nicotine that kills them. And so you will find some quote unquote green herbicides or insecticides that are based on nicotine. You can spray and it'll kill ants and bugs and all different kinds of things. Believe it or not, it is a very toxic compound. If you ingest nicotine directly, it will kill you. And the last thing that I ever looked up on it was basically if a human ate 2 cigars, it would kill you because of the amount of nicotine that's in it. And in fact, the story goes that back during World War II, spies always carried 2 cigars. So that if they got caught, they would eat them and kill them so that they wouldn't talk. Conine, a very simple amine. What kind of amine is this? It's a secondary amine, but it's chiral as well, right? There's a chiral center right there. This comes from hemlock, very poisonous. This is what Socrates was executed with. Right? They made a tea out of hemlock, he drank it, and Socrates was no more. The take-home message here is these things are more toxic than you think that they are, but yet we allow you to have access to them over the counter quite easily, right? As long as you're of the age. Well, you can't get conine, but right? We don't really control your access to caffeine. A tablespoon of caffeine will kill you. Nicotine, again, very, very deadly. And that's really the take-home message of these amines. Amines are toxic, but they are also very, very useful. This is an example of dopamine. It's a neurotransmitter. Okay? What does dopamine do for you? Makes you happy, yeah. Makes you feel good, right? It's a neurotransmitter. If you've got dopamine release, right, you start to get communication across the cells. This gives you a sense of euphoria, gives you a sense of happiness, right? Folks who suffer from depression typically take what are called dopamine reuptake inhibitors because the cells have to take this dopamine back up after it's released. But some folks who suffer from depression, they have an overactive reuptake. Their body will release dopamine, but it'll quickly take it back up. And so a lot of the drugs that we give for those that suffer from depression inhibit that reuptake of dopamine so that you have enough dopamine released in the brain to help cure that depression. Okay. So we're going to talk about one very, very ineffective way to make amines. You can make amines from ammonia. Ammonia is cheap, readily available. It's made catalytically. Interestingly enough, just for your information, the world population today could not be possible if we didn't have a way to make ammonia. Can't have 6 to 10 billion people without being able to make ammonia. What? It is toxic, but it's also used to make fertilizer. It's used to make a lot of things, but the biggest source of consumption of ammonia is in the manufacture of fertilizer. And we wouldn't be able to generate the food that we're able to generate today without artificial fertilizer. You cannot sustain over 6 billion or whatever the world's population is today with organic gardening. It's not possible. And so ammonia has the lone pair of electrons. It'll do an SN2 reaction on a primary alkyl halide, and you will get a primary amine. But there's a problem. The primary amine is actually more reactive than the ammonia. So what happens? It starts to react faster with the alkyl halide, and it makes the secondary amine, which is more reactive than the starting primary amine. So it reacts, and it makes a tertiary amine, which is more reactive, and it makes the quaternary ammonium salt. This is actually a very bad way to make a primary, secondary, or tertiary amine, but it's an excellent way to make a quaternary ammonium salt. And so this is how they make those quaternary ammonium salts for your soaps and things like that are antibacterial.
Is it a chain reaction? Like you do one thing and then that reacts to that, which reacts to that?
It's not really a chain reaction. I can see where you think that. But really what it is it's a race. So ammonia will react, but it reacts slower than the primary amine. Because remember, primary amines are more basic, secondary amines are more basic. Well, more basic also means more nucleophilic in this case. And so now that this is more nucleophilic and more reactive, it starts to react as opposed to the ammonia. And it's just a competition. Okay? So it ends up winning out. The only way to make this reaction really work practically is to use like a swimming pool full of ammonia. Huge amount of ammonia with a small amount of alkyl halide. Then you can get it to stop at the primary amine. But that's because just of dilution, right? And so that's what I'm showing you here, right? If you had a huge excess of amine or of ammonia, you could make a primary amine. But under most laboratory conditions, this would then go back and react and keep on going. But you got to use a huge amount of that, so it's not very efficient. And then, of course, you can take a tertiary amine reacted with an alkyl halide, and you can make a quaternary ammonium salt very, very easily. Okay? So, with that said, I think we're going to call it quits. We've got 2 more slides. We'll finish those up on Wednesday. Now, Wednesday, we are getting started in spectroscopy, chapter 11. You need to read that before you come, okay? You need to know about electromagnetic radiation, radio frequency. That's the first couple of pieces. I need you to be familiar with the language when I start talking about spectroscopy. All right, see you all on Wednesday. Happy Halloween.